Hey everybody, welcome to CS302 Assignment 7, and as you can see on the front of the PDF, we are going to, we're going to work on a graph theory problem where we will simulate Jill Valentine trying to escape RPD from Resident Evil 3. So if you ever played the original Resident Evil 3 game, when we first entered the Raccoon City Police Department, that's when we first encounter Nemesis. That's when things really get actually pretty interesting. So, I think when you first play the game, in Resident Evil 3, one of the nice features is when you have certain moments in the game, you have a decision to either, you have one of two choices you can make. And of course, when you first play the game, you get terrified when you first see Nemesis. So you, of course, choose to not fight Nemesis, but run into the police station. Then at some point, near the I think the dark room where there's a typewriter, there's a window right at the staircase, and that's where he bursts out with a rocket launcher and scares you pretty well actually. And that's when the game also is pretty interesting. So we're going to essentially implement this where we have our Raccoon City Police Department, and it's going to be represented as a graph. And this link right here, it will take you to the page where you can see the actual graph. Now, I actually modified it a little bit for this assignment because, well, I wanted to make it a bit more interesting or have more possible paths to be created. So I modified it, but it is based on this map right here. So let me just go ahead and just click on this and see where it takes us. Oh, there it is. So pretty much here's the first floor. And I believe in the Resident Evil 3 game, you only actually focus on this side. So actually, it's Resident Evil 2's map, but of course, it's the same police station used in both games. I think in Resident Evil 2, you spend more time in the police station than Resident Evil 3. So I think in Resident Evil 3, you only really spend time mostly on the left side. So I don't think you actually spend any time at all here with Jill Valentine. And I think you might spend some time in the second floor. Yes, you do in Resident Evil 3. You do go into the STAR's office at some point. But I'm making this, the actual graph will only contain first floor locations, only the left side, and of course, main hall will only be used in this graph theory traversal. So let's go ahead and now go into a bit more detail as to how we're going to implement or what we're going to actually have to do for the assignment. So before I go into the actual details or the structures needed for the assignment, I first want to go over and just mention that I do have the link here for the Resident Evil 3 save room music, which of course I'd recommend you to actually play that during this video. Now, I wanted to actually play it in the background as I go through the PDF, but I'm not sure if it would cause any copyright issues since it's not officially it's not my video, the theme song. So I didn't play it really in this video right now, but of course you can open this up and listen to this while I go over the assignment. And of course, as you code the assignment as well, I would, suggest to play this because it really does help you. It really helps immerses you into the actual game. So, definitely one of the defining moments in this game is when you first enter the save room. Anyways, let's go ahead and now talk about the structures needed for the assignment. So we're going to have, well, our adjacency list, but it's going to be a map because in this graph, we're going to have, well, a set of nodes, but the nodes are going to have names, like a room name, like main hall or dark room. They all have a name. So we use a map. In the string, the key is going to be the name of the room, and it's going to map you to a list of neighbors. And a list is an STL, it's a linked list class. So again, you can use this if you want to have a linked list, which definitely helps you so you don't have to actually implement your own custom linked list class. So we have a list of strings, which are going to be the names of all the rooms that are adjacent to the room that we're currently on. So adjacent means, well, we can have several doors in a room, and each door will take you to a different room. So that's each door will be, I guess, an edge to a different room, I suppose. Now, this map right here, again, we want to we're going to use maps all the way because, well, we're going to be using the room names as the ID. So we don't need to use integers. We use a string. So we have to have unrooted map, or a map would be okay too. But unrooted maps are faster in runtime lookup. So of course we'll use this instead. So this map is going to tell us really which rooms Nemesis is located in. So when you first enter that that west side of the police station, that stairwell, originally when you play the game, when you don't decide to fight Nemesis in the courtyard, he does just burst out of that window, it bursts from that window into that room, and you start fighting. And of course, the smart way to play Resident Evil 3 is to not really fight Nemesis unless you want to pick up certain sort of weapon attachments that he drops occasionally. But a smart thing is to just run from Nemesis. But of course, when you do that, as you enter different rooms, Nemesis appears randomly, and then he will keep on sort of, chasing you through the whole police station. So this map tells you which rooms Nemesis will sort of be waiting for you. So at any point in time, as you enter a new room, Nemesis could just appear in that room randomly. So we're going to mark which rooms Nemesis will appear. So we mark a room name to an integer. So if the integer contains 0, if it returns 0 for a certain room, that means Nemesis is not in that room. If it contains a positive value, the Nemesis is in that room, and the positive number tells you how much damage he's able to apply onto Jill. And then if the number that it maps to is negative, that means there is a healing item in that room. So that's going to, I guess, decrement your loss, which means it's going to increase your your health for Jill. So if a name, let's say we have a room called, I guess, a dark room. If we use a map, dark room, so we have Nemesis locations, and index dark room, if it returns 0, there's no danger. The positive value, Nemesis can apply that much damage onto Jill. A negative number means there's an herb, so it undoes the damage Nemesis did earlier, so it will heal Jill. And we'll, of course, go over how we're going to apply these to our DFS Traversal. Then we have our predecessor map, which we map a string to a string. So we want to really give the predecessor room for each room so we can construct our paths in reverse order, same way we did it in class. So of course we can go over this as well later on in the video. And then we have this map right here, which is going to map a room name to an integer amount. So this is going to serve kind of as it's going to serve as a visited array, except that it's not going to map the name of the room to a Boolean true or false, but to a number. So at any point in time, Jill enters a room, and Jill has a health amount. And we want to store what health amount Jill had when Jill entered a certain room. Now, there could be more than one possible path that leads to a certain room. If that's the case, we want to store the max health among all possible paths that leads to this room. And of course, it might not make sense right now, but I will draw out an example visually to help you see how it's going to actually work. So this is sort of our main structures needed. Let's go ahead and now discuss how do we actually construct our adjacency list or map. Okay, so in your program, you're going to actually have two input files. One will be the rpd.txt, which is going to be your list of edges. And you can also have this Nemesis file, which tells you essentially which rooms Nemesis is located in. So for example, right here in this particular instance, in the main hall, Nemesis has the value 7, so Nemesis can apply 7 amounts of damage to Jill. But dark room is, I guess, a save room, I suppose. So you have -3, which means you actually can undo Nemesis's damage by adding more health or some herbs in that room. So let's go back to our RPD file. We want to store this into a adjacency list. So for example, let's look at this right here. Let's look at this first. I think here's the case I have in the PDF. So let's suppose on this line we have these two elements. Now, you of course don't have to do any sorts of weird get line. You can use input file stream, like in file. And you can use the extraction operator or that input operator because every single line is separated by a blank space. So you can just use that technique to parse. You don't have to worry about using getLine and then using all that weird fancy stuff. Just use the input operator. Every line will have two strings on it. This will be your, the first room name will be the from and destination. So there actually is a door from west stairway to dark room. So for example, we want to add this into our list. Well, we have our map, and we're going to index it at west stairway, first floor, dot pushback dark room. Now, the way this works is because when we use this map and we pass in a name, this is going to return the value field. So the key is going to be a string, and the value is, well, a linked list of strings. So we can apply the pushback function to insert this node to the back of the linked list. So we have a node in west stairways list that contains dark room. Then of course in our file, the next line will have west stairway first floor evidence room. Well, you would just look up west stairway first floor, the bracket operator, dot pushback evidence room. So we're tail inserting nodes to the back of west stairway first floor's linked list. So for every line, you have to index it using this name, and we push back that name. And it's going to create our array of linked lists, if you will. So we have all of our nodes stacked up, all of our neighbors for a room stacked up. So we do this for every single line. So rather simple. Every line is separated by a blank space, so very easy to parse this. Now you're going to have to be able to traverse this array of links, or traverse this list of neighbors. So when we do DFS traversal, you may remember that you have to often traverse your neighbors list, and you have to go to each, you recursively call the function on each neighbor. So here's two ways you can traverse this list. So if I want to go through all of west stairway first floor, I want to go through all of this room's neighbors, well, we can use an auto type. Now, neighbor is going to be an iterator. It's going to be a list : iterator. Except the auto is easier. We don't have to worry about, including that entire data type, because really this neighbor variable is only used in this for loop anyways. There's no point to give it a type. There's no purpose because I'm not going to use this variable anywhere else in our program. So it's definitely makes it a lot more simpler. So we have our map, west stairway, dot begin, which will assign the first node to our neighbor iterator. And then while is not equal to the end of that linked list, neighbor plus plus. This loop will go through every neighbor in west stairway first floor's neighbors list. So when I say cout star neighbor, it'll output dark room, because dark room is the actual string stored in that neighbor pointer. So neighbor is really an iterator or a pointer to a node. And remember, a node contains two fields, a data and a link. So star neighbor will give us the data field. The neighbor plus plus will increment the pointer to the next node. So I say star neighbor, it outputs this time evidence room. And then plus plus for neighbor again. Neighbor will now be winding corridor. And the neighbor plus plus again will be now on west stairway second floor. So that's one way you can do it. And here is an alternative way. You can use a range-based for loop. So you can, again, use auto neighbor, and use a colon symbol, an RPD map, and of course, you want to get the list of neighbors of west stairway first floor. So now neighbor, in this case, is not going to be an iterator. It's going to be a string. It's going to essentially be the string object stored in each node. So this time around, if I say cout neighbor, it's going to also output dark room, then evidence room, winding corridor, west stairway, except here, neighbor is not an iterator, it's actually a string, because it's going to cycle through the list of nodes, and the neighbor is going to be a data field of each node. So these are two ways we can cycle through all the neighbors. Either way is fine. So I actually use this method in my program because it's definitely, cleaner code, but either one is going to work just fine. But we do need to go through each neighbor one by one, and then we have to, like in class, we have to call a DFS function on each neighbor to go through every possible path. We want to go through all the neighbors for a current room. So we can try to expand on every possible path and find a way out of the Raccoon City Police Department. So then again, I guess that's really all there is to Adjacency Map. Let's now go into the contents of main and really an idea of how this DFS function would need to be implemented. So you don't have to actually implement this exact same function, same prototype, but I'd recommend you use this because this method does work if you do write the code correctly. So this is going to be really a DFS-like traversal, a little bit modified because you might actually re-explore the same node more than one time if a better path was found. And of course, I'll draw the example here on one node so you can see how you would create that, how you would actually visualize this traversal, but I'll go over that after I just talk about the overview of this function. So I have documentation right here, but ideally you're going to have a string. This is going to be Jill's location. So this is like, when we went over DFS in class, we had that int cur. This is going to be exactly that. This tells us which room we are currently on during Jill's traversal. What room is Jill currently on? That's what that room will be. So when we first call function in main, we're going to pass in a string literal west stairway first floor. That gets passed in. We pass that string literal into this because we're going to start our traversal from this room. That's where Nemesis burst out from the courtyard when we first play the game. Now, the second parameter is going to be the room we're trying to reach. You're trying to see, so if Jill's location does equal, this room to reach, and the health amount is larger than 0, then we found a path. We found that path to the end. Now in main, we're going to call the function and pass in the literal courtyard. So we're trying to find a path literally every time from west stairway first floor to the courtyard. So you want to always find a path if a path exists from this node to that node. Now, this Jill's health variable will tell us how much health Jill has when she arrives at this certain node. And of course, whenever we go to a new node, we're going to either decrease or increase Jill's health when we go to a new node, because when we go to a new node, that new node could contain a healing item, or there could be Nemesis there waiting for us. So then we're going to have to either decrement or increment the health when we go to a new neighbor. So we always update this accordingly as we traverse the graph. So this will always tell us what's the health value for Jill upon arrival on a certain node. Then of course we have our map, our adjacency list. Without that, we can't really do anything. Predecessor, same idea like when we did for DFS. Whenever we go to a new node, we always have to mark the predecessor of our destination. So same sort of idea, same logic here. Now this is going to be a little different. So health in room, I mentioned this earlier. This is going to be really your visited array, but we're not going to map a string, a node name to a boolean, but to an int. So that int tells us so let's say we find another path. Let's say we already visited this node earlier. Well, let's say we come back to this node, but now we found a better path where this path, we actually have more health this time around. Then we want to re-explore this node. But let's say we find another path and the health that we have upon arrival to a certain node is actually less than the last time we were here. We don't want to re-explore. So I'll try to give you an idea of how you want to set this up when I show the example in a little bit. And of course, this map is going to be Nemesis locations. And of course, we use this file to populate this array. So we would just so before we call the function escape RPD, we would just literally read each line. Each line contains really, two things: a room followed by a number. So you can just insert this key and this value one by one into this map. So you would, of course, you would first set up your RPD map and Nemesis locations. You would first initialize these with these two, with this file and with this file. But this one's very simple to update because it's really just the key will be string, values integer, simple to set that up. Once you have all that, you just, pass it in. It tells you, if there's danger in a room or not. So that's basically the contents of main. So then in the program, so of course, before I move on, this Boolean function returns, or this DFS function returns true or false. So it returns a false. That means when you're on a current node and you try to pick a neighbor, it led to a false, which means it led to a scenario where you couldn't find a path to your room to reach or to the courtyard. So returning a false back means you have to resume, you have to go back to the predecessor node, and you have to try a different path. If a true is returned, that means you found a path. You have to relay true all the way back to main. But I'll go over that in a little bit. So I'm first just at least mention that before I go over the more detailed explanation of this. And essentially, here's going to be the output. So when you run your program, you're going to, of course, compile your main. You only will submit a single main file because you're not going to have to create any custom libraries. You can just include vector, include unordered map, include list, and all that. So you can just include all those into your program. And when you run your program, you pass in your two files through a command line argument. So you pass an RPD, MSS1. That's the path that leads you to the courtyard. And of course, the very famous what Jill says at the very beginning of the game, always on the typewriter, you can hear typewriters, typewriter being pressed while this sort of text appears on the screen. Now, the second Nemesis file is the same idea, except the numbers will be different in this second Nemesis file. And this way, in this scenario, a different path is constructed because, well, Nemesis could appear in different spots with different strengths, and of course, a different path you may have to construct to find a path from the west stairway to the courtyard. Third one's also another win, and the fourth one, I feel bad about this one, but here's a case where there's no way out because no matter which path you try to take, all of it leads to either there's no way to the courtyard or you run out of health. So whenever you take any path you try to take, you will actually not have enough health to make it all the way to the courtyard, which means a failure, of course. This is where Nemesis screams out stars, I guess. That's what I'll just use. So now I'm going to go ahead and just on OneNote sort of draw out how you want to code this or give you an idea of how you want to code this. So let's go ahead and do that next. I think then we should be done with the video. So let's get to it. Okay, so here's the graph of the west wing of the RPD. I can, of course, share this PDF on Canvas. I might remove the numbers maybe so you can, of course, you can work these out manually yourself on different problems. But I'm going to use the Nemesis03 txt file to set this up. So first we have an RPD file. So here's our graph, and I just simply add in all the edges in, like so. Now I use red to draw the edges. I use blue at certain times because if there were some edges that crossed, it might be easier on the eyes maybe to be able to not get confused when you see these. So now I'm going to also introduce that I'm going to mark each node. So I'm going to use nemesis3.txt to sort of mark essentially for each node, each room, if Nemesis appears in that room and how powerful he is. So for example, in the main hall, first floor, he has a value 5. So I put 5 right there. So I also put this legend right here as well. So we have these numbers in green represents Nemesis's strength. So if he has the value 5, then he can apply 5 amounts of damage to Jill. And let's say in the waiting room, there is 0. So Nemesis does not appear in that room through our traversal. And -6, like right here, implies that we have healing items, so we can add 6 to our health when we enter this room. So you want to find a path from west stairway down to courtyard. So in this Nemesis file, I think I forgot to include west stairway to the second floor. I didn't put that here, I don't think, but it doesn't really matter because, well, this node leads to a dead end anyways, so we're not going to really do anything with this. So I didn't put it here, but we can imagine that it's going to have a default value of 0 for that node. So we first call this DFS function in main. We're going to pass in the health of 20. We're going to pass in west stairway for our current position, our initial current position. Our target position will be courtyard. And we're going to pass in our adjacency list, pass the nemesis locations, and health in room. So these numbers are marked in pink initially are going to all be 0. So 0 really means that these nodes are unvisited at the moment. And as we visit them, we're going to update these to bigger values. So let's go ahead and now begin traversing this graph. Okay, so we first start off by just calling our DFS function on west stairway, like this. So this is going to be a starting point. This is where Nemesis bursts through the window near the stairway, and of course, scares the person playing the game, and you don't know how to respond suddenly, so you do take some damage from Nemesis. So at this spot, Nemesis can apply 5 amounts of damage to Jill. So we're going to subtract Jill's health from 20 down to 15. And we're going to mark this node visited by reassigning this value 0 with the value of 15, which means that's the amount of health we had after we stepped foot on this node. This is going to be our way of marking a node visited. So what's going to happen now is that, okay, so once we do this, we check. So obviously we haven't hit our destination yet, so we're going to have to now pick a neighbor. So we have to iterate through all of West Stairway's neighbors. And suppose our first neighbor happens to be Dark Room. So we're going to go to this neighbor. So our second function call goes right here. And then this function, so I guess this is sort of a very difficult version of the game because Nemesis normally can't enter a Dark Room because I think Dark Room is a safe room, but we'll make this game a little bit more harder so Nemesis can enter this room. So the value in this room is 3, as you can see with that green number. So we decrement Jill's health in this function body to be 12. So when we call the function recursively, in the previous function, we had 15 for our health. We passed 15 into the new function call. So whenever we go to a new node, we always update the health along the way. So then what happens is, okay, in this function body, we subtract 3 from Jill's health to give us the value of, well, 9. Sorry, wait, I made a mistake. We were 15, we passed 15 into this function, sorry. Subtracted by 3, we had the value 12. My mistake. So we had 20 initially, subtracted 5, we passed 15 into this new function call. In this node, we have 15 for the health, that the parameter will have 15, minus it by 3, and we have 12 now. Now, the previous number 15 is not lost. This number is actually preserved in the predecessor function, right here in this function body. That variable Jill's health contains 15. But remember, for new function call, we have a fresh parameter. So this parameter is not going to contain 15 in here, but it will contain 12 in this function body. So now what we have to do is we have to explore to a new neighbor. So Dark Room, I guess since this game is more difficult, this version, that Nemesis can enter Dark Room, I guess we also have a way out, an escape room from the Dark Room that leads us to the West office. So our third function call, we go right here. In this new function call, we passed in West office for the Jill's position, and we passed in 12 into this function call. So we're going to subtract 12 from our health to give us the value of 0. So our health in this function call is going to be 0. And we're going to overwrite this 0 with 0, because that's going to be our health we obtain at that node. So we mark this node visited, and we assign the value 0, which means that that's the amount of health we have when we arrive at this node. But you might notice that, okay, we have 0 health, which means at this room, I guess Jill would have lost. So we have to backtrack. So we return the value false back to the predecessor node that tells the predecessor node that, oh, this path did not work. So we return false back to Dark Room. So I'm going to go ahead and mark this as this function call is done. We returned false back to Dark Room. So then Dark Room, we have to remember which location, where we last left off in that function body. So we left off where we called DFS and passed in the West office. So we have to go and continue that for loop, same exact example like in class. And we see there's no more neighbors for dark room, so we have to go ahead and return false back to the predecessor function, back to west stairway. So west stairway gets the value false, so when we try to take dark room, it leads us to a failure. So we know that. So okay, well, we have to now, in our for loop, remember we call the DFS function in the for loop body, we have to now pick a different neighbor. So our other neighbor will be evidence room. So we go to that node. But what's going to happen is when we actually backed up twice, these two variables for health were destroyed because we escaped those two functions. So when we go back to west stairway, in that function body, we remember that the parameter health contained 15. We don't have to reassign, we just remember that's what the health value was in the previous function. So now what we have to do is now we're going to call our DFS on our other neighbor, which we're going to go ahead and call it, I guess, maybe next on evidence room. So our fourth function call goes right here. And we're going to pass in, we pass an evidence room into this fourth function call, and we pass in the same health value 15 that we passed 15 from this node originally. We called DFS on our neighbor dark room, but now we went back to west stairway, and now we call DFS on our neighbor evidence room, passed in 15, and then we're going to add the value 2 to our health. So our health now is going to be 17. We found 2 herbs in this room. And we're going to mark this with the value 17. That's how much health we have, because we have 15 in west stairway. We entered evidence room and we found 2 herbs, then we have 17. Okay, so now we have to again check. Well, again, evidence room is not our destination, so we haven't won yet. So then we have to, of course, continue. So now we're going to go to our neighbor west office. You might notice, well, we've already been to that node before, haven't we? So why should we go back there again? But notice that this time around, we're going to have a bigger health number than before. So when we go to this new function call, let's have our fifth function, we're going to again revisit west office. This is a little bit different from the examples we covered in class. We're going to go to this node, we're going to pass in 17. Now, in this spot, as always, this has Nemesis is already here waiting for us. So we subtract 12 from Jill's health. And now, Jill has the value 5 for the health. And we're going to mark this node with the value 5 for health in room. Because in this path, we actually have 5 units of health. Last time we went to west office on a different path, we ended up having 0. So you've already seen this node, but this path led us to a better path because we found the path from west stairway to evidence room to west office gave us a better result. So because we get a better result, it's actually worth re-examining. However, if let's say the result we had was equal to or worse than last time, there's no point. So this is actually a bit of more of a hybrid version of visited, because we might go to the same node again if we had better results than last time, and this time we did. So now from west office, same idea, we're going to go ahead and try to pick a neighbor. So suppose we try to go to main hall. Okay, so our sixth function call is going to go to main hall. And then what happens here is in main hall, we see Nemesis will be waiting for us in this room, and there's 5 units of damage he can apply on us. So we're going to decrement Jill's health to be 0. And we're going to mark this with the value of 0. So again, well, that means Jill didn't make it, unfortunately. So that means it's a failure. We have to return false back to the predecessor. So we return false back to west office. I'll try to fit this here and not make it look too conglomerated, but I guess I'll do it like this. We return false back to the previous function, and we're going to remove this value. We go back to west office, and remember in that function we had the value 5. You remembered how much we have because the parameter stores the value 5. So we had 5 right here. Okay, let's try a different path. So from west office, if we resume that loop in that function body, our other neighbor will be L corridor. So we go to that function. This is going to be our 7th function call in our order. And we enter his function. Well, we pass in 5 for Jill's health, and we're going to subtract -6. We're going to add 6 to Jill's health, so Jill will now have health of 11. And we're going to mark this with the value 11. And this is actually a bigger number than we previously saw, so we can explore this node. Okay, so we only have one. We have 2 neighbors actually, but I'm going to not choose file storage because there's no point. But your program might do that, but just to speed things up, it's a dead end anyway, so we're just gonna not pick that neighbor for right now. I'm gonna go ahead and pick waiting room. Okay, my 8th function call goes right here, waiting room. And this room has, Nemesis is not here at all, so we don't actually have to subtract anything from waiting room. And we're going to mark it visited, or we're going to mark this with the value of 11, because we have 11 health units when we got here. And now, from waiting room, we're going to pick another neighbor. Well, in the waiting room, we only have one neighbor to main hall. We've already seen main hall earlier, but the last time we were there, we had the value 0 for main hall's health. So let's see if this time we get a better result. So we're going to now go to main hall again, but we're going there in a different path. So we're kind of going there again for the first time because a different path might lead to different results. So we go to this node, main hall. We check this and we see we have 5 units of damage Nemesis can apply on us, which is going to give us the value of 6. Because we have 11 currently, we pass 11 into this function, and then we have 5 units taken away, we have 6 now. We're going to now mark this with the value 6, so we have a better path. We found a better way to get to main hall. So what's going to happen now? We go to main hall. For main hall, we only have one neighbor, the courtyard. So you can imagine our 8th function call. We arrive at courtyard, subtract 0 from our health, which is going to be above 0. And now our destination is courtyard, so we return true all the way back to the beginning. But whenever we go to a new function call, we always mark the predecessor every time. So essentially, whenever we go to the function, we always mark it. Now, of course, we have to make sure that, like over here, for example, we had a predecessor for West Office was Darkroom, but then we updated West Office's predecessor to Evidence Room 2nd time around. So you have to make sure that if a better path is found, we have to also not just reassign the health amount in that room, we have to also reassign the predecessor as well because we found a new path to West Office. So this is really the idea. So we may have to revisit a node more than once potentially, but it's okay. This health and room is really our smart visited array, which is going to really give us more details. So not just have you seen it, but what was the health that we had when last time we were there. So if we have a better health this time, we can re-explore, and then we have to, of course, update the predecessor as well. Now, of course, you can pass the predecessor as a parameter into the function also if you want. So there's really no rule. You can modify the DFS function as well a little bit and pass into predecessor, maybe even into a function call. Now, I was able to find a way to not do that, but it's really up to you. So anyway, this was really just sort of the overview or me tracing out this function. Hopefully, this gave you an idea as to how the DFS call or DFS function we did in class, how it can be rather modified slightly to work in this example. So I guess that's really it for this video. Hopefully this gave you some insight. So happy coding, and until next time.